We explore the theoretical foundations of classifier-free guidance, CFG, a prevalent method for conditional sampling in text-to-image diffusion models. Despite its widespread use, CFG's theoretical basis has remained unclear. We begin by dispelling common misconceptions, demonstrating that CFG behaves differently when combined with different samplers, like DPM and DDM, and that neither generates a gamma-powered distribution as previously believed. We then clarify CFG's behavior by showing that it functions as a type of predictor-corrector method, which we refer to as predictor-corrector guidance, PCG. We prove that in the continuous time limit, CFG is equivalent to combining a DDM predictor with a Langevin dynamics corrector, each corresponding to a carefully chosen parameter. This work provides a theoretical understanding of CFG by embedding it within a broader framework of principled sampling methods. The rate of convergence for the tail-averaged gradient descent, GD, method is determined by a few key factors that are generally linked to the properties of the objective function and the specifics of the algorithm itself, including the step size and averaging scheme. Here's a general analysis based on the conditions described. ####1. Strong convexity asterisk. For a strongly convex function with parameter tail-averaged, GD typically enjoys an exponential convergence rate. The convergence rate in this case is often of the order of exponential magnitude, where the learning rate and the iteration number are exponential. Averaging the gradients typically smoothens the convergence behavior, but doesn't change the fundamental rate. ####2. Smoothness, Lipschitz continuity of the gradient. If the function has a Lipschitz continuous gradient with constant, the choice of the step size is typically constrained to ensure convergence. The convergence rate can then be influenced by both loss and the tail averaging mechanism. For instance, with tail averaging, the variance of the gradients diminishes over time, leading to more stable and potentially faster convergence. ####3. Rate of convergence asterisk. For general convex functions, the convergence rate of GD with averaging typically scales as linear, depending on the strength of the convexity and smoothness conditions. However, for strongly convex functions, the rate improves to exponential convergence as noted earlier. ####conclusion. Tail-averaged gradient descent can provide more robust convergence, especially when dealing with noise in the gradient estimates. The exact rate depends on the properties of the objective function, e.g., convexity and smoothness, and the step size. If these conditions align well, the method can converge at an exponential rate in the strongly convex case, or at a sublinear rate for general convex functions. The averaging process generally helps in stabilizing and potentially accelerating the convergence. The analysis is consistent with known results for convex optimization methods, and the provided conditions help ensure the method achieves an optimal convergence rate under the specified assumptions. If you have specific parameters or conditions in mind, further refinement of this analysis may be possible.